Jeff, are you there?
He is here.
Hello.
Hi, Milena.
First of all, did you get my little present? You know, the box that I sent you? Do you have it?
I did. Yep, it's right here.
Have it. Please tell us what's inside.
Okay, let's have a look. Oh, it's it's a top. I wasn't expecting that. I'll be honest.
Would you please give it a spin?
Yeah, of course.
Tell us
Sorry,
what it can
I'm
do.
staring at this thing. Yeah, of course. It's spin the top. Yeah. Okay, well, I haven't done that in a minute. Okay.
But I hear you laughing, so I kind of knew that you like it because
That's true.
That's the technology that we'll be talking about today. Surprised?
I didn't realize Bosch had toys in the product portfolio.
No, not exactly. But this has to do with some technology that we'll be looking at today.
From know-how to wow. The Bosch Global Podcast.
Welcome, everyone, to the Bosch Global Podcast. Or if you're a loyal listener and have listened to all previous episodes, welcome back. Well, and considering that we're living in crazy times right now, and I guess you're all very well aware of that, we'll record this episode remotely today.
And hello, everyone else, also coming to you from my home office. So, Milena, what's on the agenda for today?
It's sensors, called MEMS, in fact, that make a lot of our electronic devices work, and MEMS can even detect wildfires, for example, or help prevent the, coronavirus infections at the moment. To understand how they work, we're going to dive deeper into the principles that keep this spinning top from tipping over, and how you can use them in tiny chips. And by the way, those chips you can actually use in toys. Well, let's say gaming devices. That's more accurate, I guess. And also, by doing the research for this episode and thinking about it, it really got my head spinning as well. Spinning.
Is that a top joke?
It's a good one, huh?
All right. Yeah, absolutely. So I'll bite on that. So why is that?
Well, I kind of realized that spinning things are everywhere. Electrons spin, atoms wiggle, and, well, even when looking at that table that's right in front of me and where the microphone is standing on, when you look at it, I don't know, it's actually not that rigid as you might think, on a tiny molecular level, at least.
Okay.
So, well, the movement of electrons, atoms, it's crucial for everything. Mm-hmm. And if we zoom out quite a bit, the same is also true for those chips that we're talking about today. They, too, move all the time. Well, in order to get to the bottom of this, we need to refresh our school physics knowledge a little bit. Sorry for that already.
Yeah, well,
Or maybe you're even excited for that.
Yeah, it's been a minute since high school, so I could certainly use it.
Let's start with the top I gave you. When it's spinning, it seems to defy gravity, right?
That it does.
There is a force that is trying to pull it down, but the top manages to resist that force. And, well, that must have to do with the spinning, because the rotation slows down the top. Well, nope. It must have to do with the spinning, because when the rotation slows down, the top does fall over.
Right.
It's the same as, well, for example, when you're on a bike. When you sit on a bike that's not moving, it's hard to keep the balance. But when the wheels are spinning, it's much easier. And when you're going even faster, it's kind of hard to fall.
Yeah, of course. You would continue in the same direction and you would need some other force to act on you to knock you over.
It has to do with the Coriolis force.
Right. It's the resistance of rotating things to continue turning on the axis of rotation. Coriolis force. Right.
Yeah, exactly.
So how are we applying that in technology?
One important use case is ship compasses, for example. These are called gyro compasses.
Okay, tell me more.
If you want to know more, I would suggest
For sure.
Let's talk to an actual expert, someone who has worked on cruise ships, rescue vessels, and container ships around the world.
Let's hear it.
I am Benedikt Funke. I'm from Munich. I'm working in the Deutsches Museum, the technical museum, and the shipping department. And in our collection, we have the world's first gyro compass that was used on board German Navy ships. And I'm taking care of that wonderful object.
Wow, that's really fascinating. Can you tell us from when this piece is?
The research for the gyro began around the end of the 19th and beginning of the 20th century. But the first usable gyro compass, the one that we have in the museum, was developed by a man called Hermann Anschütz-Kämpfe in 1904. And it was tested and brought into service by the German Navy in 1908.
Hermann Anschütz-Kämpfe. Can you repeat that, Jeff? Just
Hermann Anschütz-Kämpfe.
Nice.
So obviously these are different from magnetic compasses in that they're not using the magnetic field of the Earth, but then how do they work?
In principle, inside a gyro compass, it consists of a spinning wheel that is turning around a horizontal axis on a gimbal mounting that allows certain movements of the axis. So if we imagine this spinning wheel rotating free in space, more or less. And now comes the tricky part. While this disk is rotating, our planet is rotating as well. So what would happen now, theoretically? While the Earth is rotating, the spinning axis of our gyro will be lifted on one side. And at that point, gravity comes in, bringing the gyro back into its horizontal position. And this will happen over and over again because this gyro, this spinning disk, in fact, it just wants to rest in peace. It just wants to turn and keep its momentum. And it has to come to a point when the axis is resting in a position that is parallel to the turning axis of our planet. And that is the connection from North Pole to South Pole. So in this situation, the gyro axis will lead towards north.
That's a little hard to picture, but I think what I'm understanding is that the rotation of the wheel and the rotation of the Earth are interacting, and well.
Oh, no worries, Jeff. I learned that the inventor of the gyro compass was advised by one of his friends, and that friend was Albert Einstein. So
okay, that explains why I haven't quite gotten it yet. Okay. Then I feel a little better. Maybe a more application-related question. Why would you need a gyro compass on a ship? Or rather, why is it better than a magnetic compass?
Oh, yeah.
It's not influenced by changes to the magnetic field of our planet. And most importantly, the gyro compass is not affected by steel. So it changed the way ships are built. The gyro, we can say, somehow blazed the trail for steel as a shipbuilding material, as it allowed safe navigation on a ship without being interfered by ferromagnetic deviations that a magnetic compass would experience on a steel ship. And by this, the gyro also made navigation possible for submarines.
Okay, that's interesting. So then this technology, that's more than 100 years old. Do we really still need it in the age of satellite navigation?
We still rely on our gyro, on our compass heading, as a input for our automatic steering systems, or also as a input for our radar systems, which are very important for collision avoidance. So our radar picture is stabilized through the gyro input, for example.
And that would be the perfect bridge to our next segment. Thank you very much, Benedikt. Jeff, do you know that you have a gyroscope on you right now? Would you believe that?
I don't think you mean the top, and from Benedikt's description, they seem rather heavy.
Well, I'm not talking about a ship's compass, but a tiny gyroscope is built into your smartphone.
Helping with the navigation.
Yes, and
They're used in mobile phones, also for gaming. They can also be used for image stabilization if I'm using the camera on my phone or making a video, for example.
This is Emma Abel. Her unit at Bosch designs those tiny gyroscopes that fit into your phones.
So how is all that working inside a tiny phone that can fit inside my jacket pocket?
What we've tried to do, or what's been done, is flatten this out. We've kind of taken that spinning disc and replaced it with something that looks more like a set of combs moving up and down or moving side to side.
Well, let me try to sum that up. So picture two combs with the teeth of the combs interlocking. And there is still room between them so that they can move. Well, actually, one of the combs is fixed and the other one moves back and forth.
Okay, so we've traded the spinning for oscillating.
And then I still have this movement, I still have a velocity, which goes into the formula for the Coriolis force. And I can have a Coriolis force act on this structure. And I can measure the Coriolis force by measuring how far the structure has moved in the direction perpendicular to the oscillation.
Okay, with you now.
So at 90 degrees to the oscillation.
Got it, okay.
Perpendicular to the oscillation. Only to repeat that because I never heard of the word perpendicular before. So fascinated by
That's the opposite of parallel. So it's 90 degrees from the oscillation, like you said at the end. I think you knew it already. It's just a language topic.
Perpendicular. So bottom line, the important part is these things move, and that allows them to measure rotation.
But the next question is, what is moving them? There's no motor that moves the comb back and forth, right?
No. The sensors that we make at Bosch are electrostatically driven.
This is where the comb shape comes in. They apply an electric charge to one comb, and that moves the other comb. You know, working with positive and negative charges.
Yeah, exactly. Now we're coming back to high school physics
here. Exactly. So for me, the next question would be, why do you need a comb? Doesn't that make it more complicated than it needs to be?
I mean, it could just be one tooth on each side.
Yeah, that's what I thought, yeah.
Well, it could, but it would be much more difficult to get enough force in there. So basically the reason we make combs is to make more use of the signal that's available because it multiplies the movement or the force, and to save space.
Ah, okay, to save space, right. Well, that really makes sense because space is of the essence here.
Yeah, absolutely. So we should probably talk about how small or how big these combs really are.
Mm-hmm. Well, to demonstrate that, Jeff, did you realize that I put another tiny, tiny gift into the box I gave you? I brought you a gyroscopic sensor.
Let me have a look. There it is. Wow. Okay. Yeah. I'm glad I didn't throw the box out. Okay. Yeah. That is very tiny. I have it in my hand. It's, I would say, about the size of a grain of rice.
Yeah.
I bet if I think I'm not going to use it, so I'm going to drop it on the table. You tell me if you can hear it.
Go ahead. Did you already drop it? Because I didn't hear anything.
I did. Yeah.
You
So
did, yeah.
it's incredibly small. But it's encapsulated. So what's really inside this thing?
Well, the clue is actually in the name. These rotation sensors are one example of a class of components that are called MEMS.
MEMS, yeah. For the listeners, that can be mistaken. It's not a meme, not a memes. So we're not talking about GIFs or cat pics. MEMS.
No. No, it's MEMS, M-E-M-S, and it stands for Micro Electromechanical Systems. So micro, they're very small.
Yeah.
Even the bigger, older ones, we're talking about square millimeters rather than square centimeters. The size of the structures themselves, for a whole gyroscope, a couple of square millimeters. 2 square millimeters, 6 square millimeters, we're down around that kind of level, at least for consumer applications, so for the sort of sensors you'd find in your mobile phone or in your laptop. If we're looking at automotive sensors, they tend to be a little bit bigger than that, but
got it.
Also square millimeters. And the structures themselves that make up the MEMS, so the moving parts and the comb structures, there we're talking about microns.
So that's micrometers, 1/1,000,000th of a meter. Not quite the level of a computer chip structure, which that's at the nanometer scale, but nonetheless incredibly small.
Yes, and Emma Abel says that one tooth of one of these combs can be as thin as 1 or 2 microns. And at the same time, they're maybe 10 times as long as they're wide. So that requires a lot of precision in making them.
So that begs the question, how exactly do they make them? These tiny moving devices, they need to get assembled somehow. I'm assuming it's not exactly by tiny robots.
Well, I'd suggest it's a great suggestion, first of all. But first, let's have a look to where they make it. Sean will show us around, our Bosch hero.
Do you have any idea why, in this high-tech world we live in, anything at all works? Do you?
This is one of his videos on YouTube.
The answer is semiconductors and sensors. And here's where these smart little guys come from.
I'm about to enter one of the cleanest rooms in the world. Good thing I had a shower this morning.
Look at this. All the people in the factory, also Sean, well, they're wearing these white overalls from head to toe. Because everything has to be absolutely clean.
24/7 production, fully automated. These robots and machines are building the stuff that makes IoT possible. And how do they do it? Using IoT.
So everything is covered. The machines basically look like they've never been used.
One big thing of Industry 4.0 is human-machine interaction. Robot and human teaming up with each other. One's got the brains and the other one's got the looks, or vice versa.
I love that guy.
And dear listeners, you will find the link to this clip, obviously, and as always, in our show notes. And you know what? Sean, our Bosch testimonial, also happens to be a fantastic singer.
You name it.
I start my days, sun rays, I tap the phone, coffee's on, I mow the lawn, impressing Sean, so connected, so effective, future zone, all for me, IoT.
Let's get back to your question. How are the tiny MEMS made? Well, they are made out of silicon, a little bit like other electronic components. So you start with a slice of a silicon crystal. It's called a wafer. And then you etch structures into it. So there are robots involved in the different steps, but the moving parts of the MEMS sensor, they are not assembled. They are practically made in one go. This etching process carves them out of the silicon wafer. That's the short and simple version. Similar to making computer chips or integrated circuits.
MEMS has topology, which means after it's been made, I have high bits and low bits. And that's a big challenge for building up new layers, is that the surface that you're building them up on can be very uneven.
And of course, that's the case for any MEMS. There are not just gyroscopes, but also acceleration sensors, gas sensors, pressure sensors, well, you name it. But the gyroscope is one of the most complex.
But why is that exactly?
So one reason will be that they need to operate in a vacuum. So once they are ready, they are covered and sealed with another layer of silicon. And then the silicon wafer is cut into thousands of individual chips. Is that complex enough?
Yes, absolutely, absolutely. But also they manage to handle the production process, right? I mean, these things are being produced at a massive scale.
Oh yeah, absolutely. I mean, Bosch has produced more than 10 billion MEMS by now. It's 10 billion. But you know, challenges remain, both in the production but also in the design of the sensors.
Basically, when we make a MEMS gyroscope, we use the resonances of the structure and design the resonances of the structure to give us as big a signal as possible. We're talking about attofarads, so that's not even 10 to the power of -6 anymore, like the micro was. It's not even -9, it's not -12, it's -18. So these are teeny tiny signals, and whenever I design a mechanical structure to have a particular resonance frequency, it will also have other modes of movement and other resonant frequencies higher up in the frequency spectrum. And this is one of the major challenges of modern-day MEMS gyroscopes, is trying to have these frequencies in places where they don't bother the system, whether the system is a car or a mobile phone, whatever.
Attofarads, that's another word I've never heard before.
Which word?
Attofarads. I had to Google that.
Ah.
I had to look that up.
Do you want to tell our listeners?
I only read about it, and I even found it super complicated. But I mean, it's fascinating that she can just tell us about that in like a regular conversation. I was super impressed.
That's why we bring in the experts. So anyway, we're making sure that these frequencies are not interfering with the other components, whether it be in a mobile phone or a car.
Yeah, and vice versa. Emma says many electronic devices have something like a pulse. That could be a quartz, a piezo element that provides kind of a beat for the system. So these are moving parts as well, and they could easily spoil the measurements of the MEMS sensor.
And that's something that I find really interesting to remember. The fact that there are moving things still inside my phone. I mean, do you remember your old music player where they had the spinning hard drives? And
Sure.
you could actually hear the thing hum.
Yeah.
And in the age of solid state drives, you generally think most of these electronics now are just totally static.
Well, I guess one could argue about this, definitely.
The vibration or the oscillation which we trigger in the sensors is several microns, so several millionths of a meter. And the force that we're then trying to actually measure, so this Coriolis force, we're talking about picometers, so a millionth of a micron, so a millionth of a meter, I think. Yeah. And is that a moving part or is that not a moving part? It's all getting quite small, isn't it? But yes, I personally, one of the things I think is fascinating about them is they do genuinely move. And what you can, if you look with the right equipment, even on the outside of some of these sensors, see that they're moving on the inside.
That's fascinating. All these things moving around like they're little lives of their own. I think we need another invented for life plug here.
I mean, you're not wrong in the sense that researchers and engineers like Emma Abel are imitating nature. In a way, MEMS imitate nature. They give our devices senses like a sense of smell or a sense of touch.
A sense of gyro, if you will. No, but seriously, is there anything like a gyroscope in nature? It's unintuitive for us to think about.
The Coriolis effect, which the gyroscope used, is a physical effect which people can't necessarily feel. But for example, flies and moths do have organs which allow them to measure this effect. So maybe not quite a case of art imitating nature, but certainly being inspired by.
And we want to know a little bit more about that. So let's call another expert, Brad Dickerson at the University of North Carolina. Hello.
Hello.
Hi.
Right there.
Hey, how are you?
I'm good. How are you?
I'm all right.
So I just learned that flies apparently have gyroscopic sensors. And you are a biologist who studies this, right? So can you confirm that for me?
Yes. So that includes houseflies, blowflies, mosquitoes, any flying insect that has two wings and belongs to the order known as Diptera is an animal that has a dedicated kind of gyroscopic sensor known as the haltere.
Okay, so let's say sometime after COVID, when we can celebrate things like Halloween or Carnival in Germany again, and I want to make myself a fly costume. Where would I put that?
The waist is a good way of thinking of the location of the haltere relative to the rest of the body.
Okay, understood. So, as we had established before, gyroscopic sensors are great for maintaining balance and sensing rotation. However, flies are also known for their amazing eyes. So, why can't they rely on them for a stable flight?
The way that the visual system relays information, one, it operates on a relatively slow time scale compared to this information from the halteres.
Okay, that's very clear, Brad. Thanks a lot.
Absolutely.
So thank you for your time.
Oh, sure, no problem. Thank you I appreciate the interest.
Thank you very much. Oh wow, Jeff! I cannot wait to see you in that fly costume.
It's just gonna be dressing up as Jeff Goldblum. You guys don't know the movie The Fly, do you?
I haven't seen it.
Oh my God,
Sorry.
It's an 80s horror
Sorry.
movie. It's fantastic.
Just
Okay.
think about that fly costume again, please.
Sorry.
Really, just dressing
Off
up
topic.
I think that would suit you very well. Brad has made an interesting point there. The gyroscopic sensor is much faster than processing a visual signal. And the same is true for MEMS, right? They deliver information much faster than you could analyze a video stream, for instance.
Plus, they're much more exact. What were the units that Emma Abel was talking about again? Auto something?
Here we are again, yeah.
We're talking about attofarads. It's not even -9, it's not -12, it's -18.
That would probably be hard to derive from a visual input.
Oh, thank God, first of all, that Emma explained what attofarads mean again, because I couldn't. You're right, which is why drones or cars use sensors and not just cameras. Emma has a great example, really showing how sensitive MEMS sensors can be. Would you mind, Jeff, standing up with me?
Oh,
please.
good. Okay. Yeah, but then I'm going to choke myself with my microphone cable. Okay. I am standing.
So could you face a wall for me?
Yeah.
Okay, wonderful. Now try and turn around your own axis until you're back where you started.
Okay, so the classic 360.
Now could you try turning very slowly? 1 degree per hour to be precise.
I mean, that's going to take a minute.
Right? Not only a minute, it would take you 360 hours to complete the turn. That would be a very long episode. We can totally have that conversation in 15 days when you're done. So something that turns that slowly, you wouldn't even be able to see that rotation. It's like watching plants grow. But a MEMS gyroscope could measure this rotation, says Emma.
Imagine what a tiny force that probably is on a piece of moving silicon, which weighs fractions of a gram. And then we want to measure that with a capacitance. And that's why we're in these minuscule numbers. So if we're going down towards the resolution limit, and it's a very long measurement and everything else, then we're into zetofarads as a range, and that's 10 to the power of -21. So a 1 with 21 zeros in front of it before the decimal point comes.
Whoa.
That's incomprehensibly small.
I can hear that you're back from turning, huh? Are you?
I'm allowed to sit down, right?
Emma says it's almost like counting electrons.
That it works at all is what I find fascinating. But it does work, and it works very well, and it works in millions of cars and millions of mobile phones.
That's a wow.
Yeah.
Wow.
Well, the MEMS gyro in your phone might not actually be that sensitive, but in Emma Abel's lab, it works. So yes, definitely wow-worthy.
Okay, so now let's talk about some applications.
Oh yeah, please.
There are millions of cars and millions of phones. What are they doing?
In your car, for example, they can detect rotation in case of an accident and then launch the airbags.
Or in the stabilization system of the car, they can detect a dangerous rotation.
But they also help with everyday situations. A gyroscope can be coupled with the built-in navigation system. And then when you have a bad GPS signal because of skyscrapers around you, for example, or maybe when you're in a tunnel, the system knows whether you've turned a corner or not by looking at the signal from the gyro.
And this is presumably the same on the phone.
Actually, let me introduce our listeners to our colleague Richard. He's a Bosch expert for MEMS applications.
My name is Richard Fix, and I'm portfolio manager at Bosch Sensortech.
And what Richard is saying is that one of the most important applications for gyroscopes in consumer electronics is image stabilization. That's useful, for example, in drones. They vibrate and they can be shaken by wind, and a gyro can help adjust for this. The same happens with a camera on your phone.
I had a personal wow effect, because I mean, if you are on a very small boat on the water, on a rubber boat, and you want to take a movie, your picture is always going up and down. If you look on the movie afterwards, which you have taken with a conventional camera, you don't want to look at it, You might get sick, when you look at it. After I did that again a few years ago with the first phone, which was fully stabilized, I was amazed looking at the movie because, I mean, the software inside, together with the sensor signals, recognized where is the horizon, and the horizon was completely stable. So I was really amazed seeing movies from my smartphone afterwards, where I did not ever expect that I can even look at it.
Yeah, it's really great when you can see a video that people shot while doing really intense activities like skating or skiing. It's incredibly smooth.
MEMS make technology better. That's also the case in your dishwasher, for example. A MEMS sensor can check how dirty the water is and if fresh water is needed or not.
Obviously, that's not a gyroscopic sensor, but another type.
Oh, yeah. Yeah, sure. There are many different MEMS sensors, as I already mentioned. Pressure sensors, for example, can determine if you're on the first floor or the second floor of a building.
And the atmospheric pressure, there's that kind of sensor in phones as well.
Oh, yeah, true. Or also when you're cooking, a gas sensor in your kitchen hood can automatically adjust the fan speed. So as I said, that's just improving existing technology. But what's really exciting for Richard is the new solutions that MEMS sensors make possible.
One big opportunity is to have sensor networks. So sensors talking to each other, which are maybe distributed in certain areas. And I mean, one very important topic currently is wildfires around the world. Yeah, this is a huge damage to the nature.
Absolutely,
and a huge impact on even on our climate. But by using environmental sensors and setting sensor networks, you could get climate models for forests, you can get a risk assessment, so you can see if there is a certain risk for getting wildfires, and you can also realize an early fire detection system. Yeah, I mean, as long as the wildfire is small, it's very easy to do something. Yeah, but unfortunately, so far, we just get aware about a wildfire if it's so large that you nearly can't do anything anymore. Yeah, so that is a huge opportunity for sensor networks.
Such a great use case, yeah.
Yeah, so imagine you're putting a sensor every 100 meters or 100 yards or so, and they're all connected together to ring an alarm whenever a fire is detected anywhere within the network.
Yeah, well said. Absolutely, that's the idea.
And as MEMS have these three core advantages that they're always the best choice for this kind of thing because they're extremely small, because they're mass produced so well, they're extremely cheap, and they also really don't consume a lot of power. So you don't need a big battery for each sensor, and they don't really require much maintenance either.
Yeah, plus, they can be smart, meaning they don't need to send each measurement they're taking to the cloud because they can make sense of the measurements themselves and only send unusual values, for example.
And this means now we come to software. Yeah? With software in the microcontroller or even in the sensor itself can understand the signal and give meaningful outputs, then there is really a huge benefit. Just to make a very easy example to understand it, if you have the raw signal of an accelerometer, yeah, it doesn't tell you anything, yeah. But if the output is directly the steps you have been walking, everybody understands it. And this is what today even our sensors can directly do.
And even though doing those calculations costs energy, battery power, they can be very economical. You can even equip a sensor with artificial intelligence.
There is one huge trend currently, which is called edge AI. So artificial intelligence on the edge means nothing else than that it's directly in the sensor.
Yeah, by the edge, they mean from the perspective of the network, the AI is on the outer side of that.
That really brings me back to that great use case that Richard mentioned. I mean, wouldn't it be great if hundreds of thousands of little helpers would monitor forests and alert us if there would wildfire occur?
Yeah, it absolutely makes sense. And there doesn't really seem to be another way of doing this. The sensor network would at some point become a part of the Internet of Things. Right. And little smart devices and sensors that are all communicating with each other seamlessly and working in the background, ideally unnoticed.
Right. And a defining component of the Internet of Things is that interface, that connection between the physical world and the virtual world. There's a transformation from analog signals to digital signals, which you couldn't even do without MEMS. So they really make the Internet of Things possible.
Do we have some more examples of some novel applications that are inspired by our MEMS?
You bet. One application that keeps Richard and his team busy at the moment has to do with the coronavirus. Just to make that clear right away, the sensors cannot detect the virus. But they can analyze the air in the room and tell you to open the window when there are too many aerosols floating around, which is so cool, I think.
Yeah, for sure. By aerosols, she means the little bits of moisture that we're exhaling and are believed to transmit the virus.
And a gas sensor can help to make you aware of them. They can measure a whole bunch of gases that we exhale.
Volatile organic compounds, the abbreviation is VOCs, which is used. Yeah? Volatile organic compounds is a very large group of hundreds of different gases, But the good thing is, if you have a VOC sensor, it is sensitive to nearly all those VOCs. And the background is the following. What we actually want to breathe is fresh and clean air. This means we want to breathe oxygen, nitrogen, and a reasonable amount of humidity. This is what we consider as clean air. Everything which is additionally in the ambient air is most likely a pollutant, yeah? And if you have a sensing principle, like VOC sensors, which can detect nearly every pollution, you have a very broad field what you can detect. And this is the reason why this sensing principle is also considered as an air quality sensor.
So too many pollutants in the room, that would mean that there's also a higher likelihood of aerosols potentially carrying the coronavirus if someone in the room is infected. So time to ventilate then.
Milena?
Yep.
We've been recording for quite a while now. Before we open the windows...
Is it time to wrap up?
Yeah, I think so. So what really wowed you today?
Well, when I started researching and doing research for this episode, I didn't know how many MEMS sensors there already are in our devices and cars, and that there could be many more in applications that just wouldn't be feasible without them.
Small things, big impact.
Yep.
I gotta say, I didn't realize that some of the remaining moving parts in my phone were just miniaturized ship compasses, nautical compasses. That's helping with the navigation and making my videos look good. So yeah, I'm gonna have to keep that in mind next time I'm trying to video one of my deadlifts.
Well, okay then. Now that you've mentioned it, let's get some fresh air. So everyone, until next time.
Talk to you all soon. And one more advice to our dear listeners. As always, in our show notes, you'll find some more details like photos and video clips of the MEMS and how they're produced. And for the German listeners, and Elena, maybe you can repeat this auf Deutsch, there's a link to Mighty Micro, the Bosch podcast, which is the whole universe of semiconductors.
Ihr findet einen Link zu Mighty Micro in den show notes. And to, get back to English, I learned a lot about semiconductors, which can be useful in clothes and even as body implants. So this is episode 5, when Manu, our dear colleague, talks with her guests about wearables in the Mighty Micro podcast.
From know-how to wow. The Bosch Global Podcast.
So very last question that I'm interested in. Which one is your favorite MEMS sensor, Emma?
I like the gyroscopes. That's what I started with, and that's still what I like best. But unfortunately, they're also among the most complicated, and it's really difficult to explain without a picture. I like that it's complicated, to be honest. That's one of the things that motivates me, is that it's not easy. There's a lot of potential for learning.